Hi everyone, today we're going to be talking about 3.12, the photoelectric effect. The photoelectric effect describes the interaction between light and a metal surface. And so what happens is when light strikes the metal surface, an electron is emitted from the metal. In other words, it's ejected from an orbital. And you essentially will ionize that sheet of metal. And a consequence of this is when light, or a photon, right, a particle of light, is absorbed by an atom or molecule, the energy of the species, that being the atom or molecule, is increased by the amount equal to the energy of the photon. So if I have a photon come in at a particular energy, my atom or molecule will increase in energy by that same amount. And equally, a photon emitted from an atom or molecule will decrease the amount of energy by that same amount. And so this is related to topic 1.6 we learned earlier, which is photoelectron spectroscopy. And so this is the principle, this is essentially the light principle, or the electromagnetic principle of what's going on in photoelectron spectroscopy. And so here we see we have our light that comes in, it's going to strike our metal. And what will happen is that these electrons will then be ejected from that metal. So if you have low energy, in the case of this green light here, rather, if you have very low energy, in the case of this red light, you get no electrons, right? The energy is too low. If you get medium energy, you get some electrons being ejected, but they are at a pretty low velocity, and they have low energy. If you have high energy, in the case of this blue light here, what you see is that those electrons are ejected with much greater force. They have a lot more energy. A few important summary points here about the photoelectric effect, just so we have in mind, is that the energy of our photon, otherwise known as a light, must meet the minimum energy required to eject an electron. If you are lower than that energy, then the electron is not ejected. In other words, the light just bounces off, or it might be absorbed, but you don't get any electron being emitted. Another consequence is the rate of emission of photoelectrons. This is just another word to say electrons that were emitted using light, is called the photoelectric current. And that photoelectric current is proportional to the intensity of light, or the energy of the light. Right, and so the rate of how often your electrons are emitted is directly proportional to the energy of the light that hits that metal surface. The last point I want to make here is that if the minimum energy is met, in other words, you have enough energy to emit an electron or eject an electron from an orbital, the kinetic energy, or Ke, of the electron is dependent on the energy of the light. Right, and so all we're really trying to say here is that you need and I'm going to write this in blue, a certain amount of energy is required to eject electrons, and the energy of the electrons is proportional to the energy of the light. That's the biggest point that I'm trying to make right here. Now, because of the photoelectric effect and because of the observation that energy is proportional, the energy of the photon is proportional to the energy of the electron that's ejected, there's a few conclusions that we can make here. The biggest one being that energy of photons is proportional to frequency. And it's proportional using this equation here. E equals h times nu, which is lowercase Greek v, where h is known as Planck's constant. And this is equal to 6.626 times 10 to the minus 34 joules times seconds. That's the constant that makes this proportionality legitimate, right? So I can write E is proportional to nu, or frequency, and nu is equal to the frequency. And this is measured in hertz, or seconds to the minus 1, or 1 over seconds. All of those are equivalent to each other, but generally we report frequency in hertz. And so because of the photoelectric effect, we can make this relationship right here. Now, in the last lecture, we also talked about the fact that wavelength, lambda, is anti-proportional to the frequency, right? 1 over nu. And so my wavelength is proportional to 1 over the frequency. And so if that's the case, then we can do a little bit of interesting algebra. If energy is equal to Planck's constant times the frequency, and the speed of light, c, is equal to the wavelength times the frequency, we can rearrange this to say that frequency is equal to the speed of light divided by the wavelength, and therefore we can now just plug this in right there. We can say the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. All right, and I'm going to define all of these terms here just so we don't forget them. So E equals photon energy. Remember, photon is just another word for a particle of light. Lambda is equal to the wavelength. And I should say this is in joules. Wavelength is typically in nanometers. C is the speed of light in meters per second, which is equal to 3.00 times 10 to the 8th meters per second. That's a constant. I had stated on the last slide that Planck's constant is h, so h equals Planck's constant. Units on those are joules times second. I'm not going to write out the actual number because it's in the last slide. And then finally, nu is frequency, which is in hertz, which is also just 1/2. And so all of these terms can be used to describe light, and we can use this in order to figure out important information about the energy of a light and the energy required to eject an electron from a metal surface. So let's just do one quick little practice problem together to end off this video. And so in this practice problem, I'm told a metal surface is exposed to light with increasing frequency. That means nu is going up, it's increasing, and the energy of photons, right? Energy of photons. And so nu and E are both increasing. Electrons first begin to be ejected from the metal when the energy of the photon is 3.3 times 10 to the minus 19. And so this is our minimum energy that I was talking about, right? Anything lower, you're not going to get any electrons being emitted because it's the minimum energy. So we're asked, what is the frequency of light when a photon, with the photon energy of 3.3 times 10 to the minus 19 joules? Well, we know that E, the energy, is equal to h, Planck's constant, times nu. So we can rearrange this to say nu, the frequency, is equal to the energy divided by Planck's constant. And so this would be equal to our energy is 3.3 times 10 to the minus 19th joules divided by 6.626 times 10 to the minus 34 joules times second. And this would give us 5.0 times 10 to the 14th hertz, or I should really write per second, 1/2, second to the minus 1, which is equal to 5.0 times 10 to the 14th hertz. Now we're asked to calculate the wavelength, and we know this relationship here, the speed of light is equal to our wavelength of light times the frequency. We know our frequency, and the speed of light is a constant. So if we want our wavelength, or lambda, that is just equal to the speed of light divided by the frequency. And so this would be 3.00 times 10 to the 8th meters per second divided by our frequency is 5.0 times 10 to the 14th per second, right? Hertz is seconds to the minus 1. This would be equal to 6.0 times 10 to the minus 7th meters. And of course, we always measure wavelength in nanometer. And so a nanometer is 10 to the minus 9. And so this would be 600 nanometer. Lastly, part C is asking us, what is the color of this light? If we look over here at this electromagnetic spectrum, all we need to do is find where 600 falls, and we can see that that is right here between 590 and 620. And so this would be orange light. And so that's how you would kind of solve this problem of figuring out the frequency of a photon as well as the wavelength given the energy. We'll do a little bit more practice in class, but for now, that's all. Thanks, guys.